Hello students, welcome to the short video lecture series on problem solving from IIT JAM Physics question papers. Today we are considering BJT Biasing, problems given on BJT Biasing. So IIT JAM 2015, this problem is given. See, this is an NPN transistor circuit. The circuit has VCC 10 volts. Beta for this NPN transistor is given to be 100 and you are asked to find the collector voltage. This can be solved by applying Kirchhoff's laws to the input section as well as output section. Applying KVL to the input section, we get this, call this as VB minus IBRB and VB. You know this VB is 0.7 volts. So from this equation, IB is equal to VB minus VB by RB. VB is 0.7. Even if VB is don't given in the problem, you can assume conveniently that VB is 0.7. Unless otherwise, they say VB is to be neglected. So 5 minus 0.7 by 100k, RB is 100k. You get 4.3 by 100k, 100 into 10 cube, which becomes 0.043 milliamps, 43 microamps. So similarly, by applying KVL to the output section, VCC minus ICRC, IC the current flows here, and this is what? VCB. VCC minus ICRC minus VC is equal to 0. From that, we are asked to find VC. VC is equal to VCC minus ICRC, 10 minus IC is 4.3 milliamps. IC, you get IC from this relation, beta IB. Beta is given to be 100, 100 into 0.043 milliamps, you get 4.3 milliamps. That IC is substituted here, and you get RC 1 kilo ohm, so you get 10 minus 4.3, which becomes 5.7 volts. In solving these two equations, you must imagine, you must know that giving VCC like this means there is a battery connected like this. If you keep this thing in your mind, you can easily write the loop equation, output loop equation. Okay, anyway, by solving this, we got VC is equal to 5.7. This problem appeared in IIT JAM 2016 question paper. This is a potential divider bias circuit. Here in this I should given below, the collector to emitter voltage VCP is asked to find. Here they are saying that VB, you can neglect VB, take beta of the transistor to be 100. So to solve this problem, first we have to simplify this circuit. This can be transformed into a simpler circuit of the previous type by using Thevenin's theorem. Applying Thevenin's theorem to the input circuit, input loop, we can get a circuit like this. Here VTH is VCC. This VCC is effectively applied like this. This VCC is across R1 and R2, forming a potential divider. So the voltage across R2 is the Thevenin's voltage, which is also called VB. That can be obtained by using VCC into R2 by R1 plus R2. And Thevenin's resistance, we want to transform this into a simpler circuit of previous type. That can be done away by using Thevenin's theorem, by applying Thevenin's theorem to the input circuit. On applying Thevenin's theorem with respect to this pair of terminals, we get VTH 5 volts and RTH. RTH is the resistance that appears when it is seen from these two terminals by short circuiting the batteries connected in the circuit. So when you short circuit this, by looking from these two terminals, these two will become parallel. So RTH is R1 R2 by R1 plus R2. You get RTH 2.5 kilo. So by putting these values here, you can easily solve this circuit. So now we apply our KVL to this circuit. So by applying KVL to the input section, you have an equation VB minus IBRB, the base current into RB, and VBE here minus IE into RE. So this loop, input section loop, consists of VB, a potential drop in the resistance RB, IBRB, a voltage across base intersection VBE, and a potential drop across the emitter resistance RB, which is given by IERB. All these voltages and drops comprises input loop equation, and that gives you this equation: VB minus IBRB minus VBE minus IERB. And it was given that VBE we can neglect, so that becomes VB minus IBRB minus IC into RE. To solve the problem, to reduce our work, we can make another assumption. We can make another assumption that IE is nearly equal to IC. IE and IC are nearly equal, so in place of IE, I place IC. So the equation becomes like this, and now I substitute IC is beta IB and IB is IC by beta. I substitute this, replace this IB with IC by beta, and I take out IC common from this IC by beta and this IC. I take out IC common, then becomes RB by beta plus RB. And now from this IC is equal to VB by RB by beta plus RB, I have this VB is nothing but Thevenin's voltage, which I got in previous step to be 5 volts, and RB by beta 2.5. RB is nothing but Thevenin's resistance obtained from this formula, that's 2.5K, 2.5K by 100, plus your RE is 10 kilo ohm, that I have substituted, and upon simplifying I get approximately out to 0.498 milliamps. I have approximated it as 0.5 milliamps. Our aim is to find collector to emitter voltage VCE. So for that we need to write output loop equation. So from KVL to the output loop equation, I get VCC minus ICRC minus VCE minus IERE. As usual, I make this small approximation. IC is nearly equal to IE. So that makes my equation somewhat simpler. VCC is equal to minus IC into RC plus RE minus VCE. You are not going to get any error by making such an approximation. So VCC minus IC into RC plus RE minus VCE is equal to 0. Our aim is to find VCE. VCE is equal to VCC minus IC into RC plus RE, where VCC is 10 volts, minus IC is just found 0.5 milliamps, and RC 5 and RE 10 kilo ohms. Of course, it is 15 kilo ohms. This 10 power minus 3 and 10 gets cancelled. You have 10 minus 15 into 0.5, you get 7.5, and 2.5 volts is the VCE. That's the answer for this problem.